Good afternoon, everyone. I'm going to present some issues that hamper the representation of high-latitude boundary layers and high-latitude climate in general in climate models, and progress that has been made over the last couple of years. And I'm going to present a model evaluation study using mosaic data that I've carried out with the collaborators listed below. So I think that three of the core issues for representing the high-latitude boundary layers and thus high-latitude climate in climate models are related to stable boundary layers, mixed phase clouds, and the representation of snow and sea ice. So we have known for years that large-scale models have the tendency to overestimate turbulent mixing under stable stratification. And of course, that causes biases in the Arctic surface energy budget and near surface temperatures and surface temperatures. And the Gables project has done substantial work on that, understanding those issues in the parameterization and alongside work on why that excessive mixing was needed in some cases to improve the representation of the large-scale flow. CM5 models have tended to underestimate supercooled liquid water. So cloud condensate was frozen at too warm temperatures in these models. And we know that has important implications for cloud feedback and thus climate sensitivity. And the representation of snow and sea ice is not well constrained, and we've seen repeatedly that it has quite strong effects on near surface temperatures and their representation in models. So I mentioned that supercooled liquid water was not very well represented in CMIP5 models, and quite some developmental work has gone into improving that. And one of the results was, as was somewhat anticipated, an increase in the extratropical low cloud feedback. So in this analysis by Max Zelinker and colleagues, we see that the extratropical shortwave feedback has turned more positive, both in terms of cloud amount and cloud optical properties, so the scattering feedback in this analysis. And that is a key contributor to the higher climate sensitivity in CMIP6 models, which we tend to think is exaggerated, at least when it comes to the high end of climate sensitivity in CMIP6 models. So are we making progress in representing the core processes in high-latitude boundary layers and models? As I mentioned, there's been substantial model development in CMIP6 to address that lack of supercooled liquid water. And a number of models have introduced more sophisticated mixed phase microphysics over the last years. And that has led to a reduction of the Southern Ocean radiation bias in CMIP6 compared to CMIP5. But we also see that the equilibrium climate sensitivity and certainly the high end of the distribution in CMIP6 has become unrealistically high compared to paleogrid constructions. And we also see that models that have small biases, for example, in Southern Ocean top of atmosphere radiation, tend to have large compensating errors when it comes to more process-related diagnostics. So for further progress, I think we should really focus on process level rather than bulk diagnostics. So this is focusing on the mixed phase clouds, which I think have been more analyzed in CMIP6. I'll show some preliminary work on the representation of stable boundary layers in a couple of CMIP6 generation models. We do have a large amount of observational data, not least through the efforts of the Year of Polar Prediction community. So we have the mosaic data, the COMBL data, all the data from YOP-SITEMIP, the HALAR FE3 aircraft campaign earlier this year, and a number of campaigns that have targeted Southern Ocean clouds over the last couple of years. But it's not always straightforward how to actually turn this great observational data into physically consistent model improvements. And a strategy that I would like to propose for that, and from which I want to present a case study in the remaining time of my talk, is to use climate models in a nudged setup. So nudging means that we relax, in this case, the atmospheric circulation at each model time step towards the circulation reanalysis, ERA 5 now a study. And we do that only above the boundary layer to leave the near surface to be freely determined by the model itself. And in this setup, we only nudge divergence and vorticity. So all the other variables evolve unconstrained, and the model can actually develop its own biases there. In this case study, we used two versions of the RV climate model which is the FESOM sea ice ocean model, coupled either to ECHAM or the OpenIFS. And we also have some results from CAM6, which is a slightly different nudging setup. CAM6 is not a spectral model, so we're nudging the wind components U and V instead of divergence and vorticity. And CAM6 is around an atmosphere-only setup without coupled ocean, and is also nudging temperature above the boundary layer. So this is showing the evolution of temperature over the mosaic site in April 2020. I'm sure the graph will look familiar, at least to some of you. We see the cold and dry air masses dominating the site in early April, 2 moist intrusions arriving in mid-April, and then stabilization of colder temperatures, which are, however, substantially warmer than at the beginning of the month after the warm intrusions. And this temperature evolution of the observations from mosaic, shown in black, and the different models shown with the colored lines, shows us that the models really reproduce the distinct weather regimes observed over the site. And that is quite significant because it means that we can use observations to evaluate climate model output on a day-to-day basis, one by one, without developing more complex diagnostics or building long-term statistics. For example, we can look at the surface energy budget and its different components in the observations and in the model, from the short-wave radiation near the surface, the net short-wave radiation on the cloud cover. We can analyze the surface albedo, the skin temperature. We can look at the turbulent surface fluxes. Now we do this again in a more statistical framework, but using the same data, and the observations again are shown in black. And you can see that when the near surface temperature gradient is positive, so the atmosphere is warmer than the surface, we have downward turbulent heat fluxes. And again, those are substantially stronger in models than they are in observation. So that suggests that at least for the couple of models analyzed here in that case study, we still see that issue of overestimation of turbulent heat fluxes in observation. And I think there's a broader analysis of this with forecast models, also for the mosaic observations, that will also be presented to you in this meeting. There's one distinct issue that we see in the representation of snow temperatures and their diurnal cycle during a couple of days at the beginning of April. So the observations show a distinct diurnal cycle here, which is only captured by CAM6, but not by either of the RV models, despite all models having a reasonable representation of the surface energy budget and its diurnal cycle. And we attribute this to the simplistic representation of snow temperature in the RV models, which only have one layer snowpack. So the surface temperature has a considerable thermal inertia, which is probably much larger than in reality, where, as you can see in the observations on the lower right panel, the diurnal temperature cycle in snow is very pronounced near the surface, but then gets progressively weaker deeper inside the snow. And CAM6 has a 3-layer snow model, which probably better captures this depth dependence of the diurnal cycle in snow. Or we can also use this to look at the representation of clouds and cloud condensate. Looking here at most of April 2020 of the mosaic site, and we see that in the cold phase, ECHAM overestimates somewhat the amount of cloud liquid water compared to observations, whereas the IFS largely lacks liquid water, and you see a bit of an opposite signal in cloud ice. So ECHAM might be compensating with an exaggerated amount of cloud ice here, to actually then in the end achieve reasonable short-wave radiation near the surface. ECHAM also happens to underestimate cloud cover in that period. So the cloud's pretty much a bit ubiquitous in the radar signal, but we only have partial cloud cover in ECHAM. And both models have a rather realistic amount of liquid during the moist intrusions. In RVCM3, we also had the data, so the IFS coupled to FESOM, we also had the data to look at the vertical extent of clouds, and that suggested that the clouds are reaching too deep in the model compared to observations, which also matches earlier model evaluations of the IFS with Arctic summer campaigns. So we conclude that, of course, cloud phase is important for climate, and we should strive to better represent that in models. And despite some improvements in bulk diagnostics, the related feedbacks are probably now unrealistic in CMIP6. So tuning has apparently introduced compensating errors, and we really should work on improving the process representation. And that is true for the cloud processes as much as for the stable boundary layers, where according to the little data that I've shown today, we might not even see as much progress since the last generation of climate models. And on the other hand, we have those recent field campaigns that really provide us a very rich data set on mixed phase cloud systems and on stable boundary layers. And we should make the most of that for model improvement. And one way forward that I can strongly advocate for is to use those nudging setups with climate models, including coupled climate models, to really improve, to really exploit that data as much as we can for model improvements. And so if you have a climate model that you might be interested in running in such a nudged mode, or if you might be interested in evaluating some of those model outputs, maybe with an observational campaign that you're involved with or that you're interested in, then please get in touch. I really hope that we can carry on some of that work after the official end of the year of polar prediction as a community effort.
Okay, I'm not clear if Felix is online. Are you there online? Should have asked this question before I stood up, shouldn't I? Okay. I don't know if he's got a working mic. We've got a couple of minutes for questions. Any questions online or in the room?
It's about compensating error. Felix, you mentioned that essentially there are developments, improvements in the models, but they are really due to compensating errors. Do you have an idea how to identify essentially these compensating errors in the verification exercise?
Okay, well, we'll maybe let him type that answer. And people can look at it online. Or can you speak, Felix? Do you want to answer that?
Yeah, sorry, I think I just got the possibility to speak, but in that moment I missed the second half of the question. So it was how to identify any compensating errors. Is that right?
Yeah.
So I think sites where we have lots of measurements of many different variables, such as like in the mosaic experiment, are a really good chance for that, because we can target a number of observable at once and very quickly go beyond sort of the very integrated bulk measures like top of atmosphere radiation, which you can measure from a satellite, but then you don't know whether the overall radiation is because of the right amounts and properties of clouds at the right times and in the right regimes. Whereas, having sort of more process-related observations and working with the models to be able to evaluate with them with those observations, I think makes it easier to identify such compensating errors.